We'll start with the oxides of carbon. Carbon monoxide with the chemical formula CO, and carbon dioxide Carbon monoxide is a colorless, odorless gas that is nearly insoluble in water. The carbon monoxide molecule contains one sigma bond and two pi bonds, as shown in the illustration. There are several ways to prepare carbon monoxide. The first way is the direct oxidation of carbon in a limited supply of oxygen or air. The reaction shown here is an example of incomplete combustion. Another way to prepare carbon monoxide is the dehydration of formic acid, also known as methanoic acid, with concentrated sulfuric acid at 373 Kelvin. On a commercial scale, carbon monoxide is prepared by passing steam This reaction produces carbon monoxide and hydrogen. This mixture of carbon monoxide and hydrogen is called water gas or synthesis gas. If air is passed over hot coke, nitrogen is produced along with carbon monoxide. The resulting mixture of carbon monoxide and nitrogen is called producer gas. Water gas and producer gas are important industrial fuels. The carbon monoxide in these mixtures can undergo further combustion. This produces carbon dioxide and liberates a great amount of heat. Carbon monoxide is a powerful reducing agent. When exposed to metal ores, it reduces most of them to the elemental form of the metal. Note that carbon monoxide cannot reduce the alkali and alkaline earth metal oxides, aluminium oxides, and the oxides of certain transition metals. Reactions with carbon monoxide are used to extract many metals from their ores. The reactions here show iron 3 oxide and zinc oxide producing iron and zinc. In the process, carbon monoxide is oxidized to form carbon dioxide. Since the carbon in CO has a lone pair, it can act as an electron pair donor. Therefore, carbon monoxide can react with certain metals when heated to form metal carbonyls. Several types of metal carbonyls are illustrated here. It binds to the Hem group of hemoglobin 300 times more strongly than oxygen. The hemoglobin molecule is, thus, prevented from transporting oxygen. This can ultimately lead to death if not treated promptly. Home carbon monoxide detectors are available and can be life-saving. Now let's turn our attention to carbon dioxide. Carbon dioxide is also a colorless, odorless gas, but it is non-poisonous. It has very low solubility in water. By volume, 0.03% of the Earth's atmosphere is carbon dioxide. Try to answer this problem on your own before proceeding. Consider the carbon dioxide molecule. What is the hybridization of the carbon? How many sigma and pi bonds are present in the molecule? The carbon in CO2 is sp hybridized. The molecule has a linear geometry. As shown in the illustration, the sp hybrid orbitals overlap to form a sigma bond with each oxygen atom. Each unhybridized p orbital on the carbon overlaps with an orbital on each oxygen to form a pi bond to each oxygen. Notice that the pi bonds are at an angle of 90 degrees to each other. The most important Lewis structure for carbon dioxide has both the oxygen atoms double bonded to the central carbon atom. The carbon-oxygen bonds are 115 picometers in length. The carbon dioxide molecule is non-polar. Although the carbon-oxygen bonds are polar, the bond dipoles cancel. Two other resonance structures shown here can also be drawn for carbon dioxide. There are several ways to prepare carbon dioxide. One way is by the combustion of either carbon or carbon-containing fuels such as methane in excess air. In the laboratory, carbon dioxide can be prepared by reacting dilute hydrochloric acid with solid calcium carbonate. On a commercial scale, carbon dioxide can be prepared by heating limestone, CaCO3, until it decomposes. In water, carbon dioxide reacts to form carbonic acid, H2CO3. Carbonic acid is a weak diprotic acid. It dissociates in two steps. First, carbonic acid loses one hydrogen ion to form a hydrogen carbonate ion. Then, the hydrogen carbonate ion loses its hydrogen ion, resulting in a carbonate ion. Both carbonic acid, a weak acid, and hydrogen carbonate, a weak base, are present in blood. Having a weak acid with its conjugate base forms a buffer system that maintains blood pH between 7.26 and 7.42. It is very dangerous for the blood pH to fall below the normal range. By using chlorophyll, plants make their own food through photosynthesis. This process removes carbon dioxide from the atmosphere. The ultimate product of photosynthesis is the glucose molecule C6H12O6. Heat from the sun warms the earth. Radiation is re-emitted and then reflected by the Earth's atmosphere. This is called the greenhouse effect. There are increased concerns that rising CO2 levels in the atmosphere may be contributing to global warming. Dry ice is the common term for solid carbon dioxide, which can be formed by allowing liquefied carbon dioxide to expand rapidly. It is used as a refrigerant for ice cream and frozen foods. Carbon dioxide has many uses. It is used to prepare carbonated beverages. Because it is heavy and does not support combustion, it is used in fire extinguishers. It is also used in the manufacture of urea, CN2H4O. Quartz has piezoelectric properties. This means that quartz can generate an electric field when mechanically stressed. This property of quartz is used to manufacture extremely accurate clocks. Quartz is used in modern radio and TV broadcasting as well as in mobile radio communication. Silica gel is used as a drying agent and as a support for catalysts and chromatography columns. Kieselguhr, a form of amorphous silicon, is used in filtration plants. Silicones are another important class of silicon compounds. These organosilicon polymers have a monomeric unit of R2SiO, where R is an alkyl group that repeats many times. Let's see how silicones are manufactured. First, methyl chloride, CH3Cl, is reacted with silicon in the presence of a copper catalyst to form methylated silicones. In addition to the dimethyl dichlorosilane shown here, trimethylchlorosilane and tetramethylsilanes may also be produced in small amounts. Next, the dimethyl dichlorosilane is hydrolyzed, as shown in the reaction. Finally, the straight-chain polymer is formed by condensation reactions. To control the length of the polymer, adding trimethylchlorosilane blocks ends the chains. Silicones are water-repelling in nature. Due to the repetition of non-polar alkyl groups along the chain. This makes them useful for waterproofing fabrics. Silicones generally have high thermal stabilities, meaning that they are stable in high temperatures. They have high dielectric strength, which means that they can withstand high electric fields without breaking down. They are essentially inert chemically. They are resistant to oxidation and to most chemicals. These properties of silicones make them very useful. Silicones are used as sealants, greases and electrical insulators, as well as for waterproofing fabrics. They are also used for surgical and cosmetic implants, as they are biocompatible. Silicates are another important class of silicon compounds. Many silicates are found in nature, including feldspar, zeolites, mica, and asbestos. The main structural unit of silicates is the ion, SiO4-4. This polyatomic ion has a tetrahedral geometry around the central silicon atom. The tetrahedral units of silicates may be joined together at the corners by sharing oxygen atoms. Silicates are thus able to form chains, rings, sheets, or three-dimensional networks, as illustrated here. Two important silicates are glass and cement. Aluminosilicates form when aluminium atoms replace a few silicon atoms in silicon dioxide. Since an Si atom with a +4 oxidation state is replaced with a +3 aluminium ion, cations such as sodium ion, potassium ion, or calcium ion are needed to balance the charge. Zeolites are hydrated aluminosilicates. They are microporous, with tiny cavities in their structures as shown in the illustration. Zeolites have a variety of uses. They are used as catalysts in the petrochemical industry. For example, in the cracking of hydrocarbons. They are also used in isomerization reactions. For example, ZSM5, shown here, is used to convert alcohols directly into gasoline. Zeolites are also used as ion exchangers to soften hard water, that is, water with a high mineral content, especially calcium and magnesium ions.